Hello, my name is Dr. Ryan Falkenstein Smith. I'm a research scientist at the National Institute of Standard Technology in the Fire Research Division in the United States of America. Today, I'm going to be talking about the equivalence ratio concept in fire safety science. Fire experiments cross a wide range of scale, from a slop burner of a single line with natural gas to prescribe forest burns to study WUI's impact on a community. There's a wide range of experiments. As a postdoc for Dr. Kevin McGrattan in the Fire Research Division at NIST, I was tasked with providing a model validation data set for a simple pool fires. Pool fires are well defined and typically burn in an open atmosphere. What you're seeing here is a GC, or a gas chromatograph, used to sample gas inside the flame envelope and a little bit in the overfire region to determine the concentration of major gas species. The results for different fires are shown to the right. When we start thinking about the scale of experiments, if I were to do simple single point gas species measurements from a single location for scales that are a little bit bigger than a pool fire, like a doghouse, a standard compartment, or even a wildfire, what could I really conclude? Could I conclude major things from those species about how the flame has been generated forth? Can I talk about how different unburned fuel is within the environment? One thing that people start to do when they start looking at larger scale experiments is the yield, or generation of species. Yield essentially is the mass of some toxic combustion product, or any product for that matter, relative to the mass of fuel that's been burned. At the National Fire Research Laboratory in Gaithersburg, Maryland, NIST, where I work, we have something called the Fire Calorimetry Database. In this database, yields of combustion products from various burns of various sizes, such as compartment fires or two-story structures, or even something as a simple payload, that are burned underneath the hood system, the yield data is specified, mainly for carbon monoxide, carbon dioxide, and soot. That information is very valuable for a lot of fire protection engineers who get an idea of the toxic combustion products that are generated from those burns. When we start to think about toxic combustion products, and we start thinking about the generation of these species, mainly in terms of yield, how does it translate across different scales? Many have attributed to the generation of toxic combustion products to ventilation, which significantly influences fluid dynamics and fire development within an enclosure. For decades, the equivalence ratio has been implemented as a metric to characterize ventilation, and therefore a means to predict toxic combustion product yields. In this presentation, we'll go over various definitions. The main one shown here in the slide, which is the actual fuel to oxidizer ratio over some stoichiometric fuel to air ratio. By definition, when phi is greater than 1, it implies a fuel-rich mixture. When it is less than 1, it applies a fuel-lean mixture, based on where you're sampling from. Over the years, other definitions of the equivalence ratio have been defined. Pitts developed a concept of the global equivalence ratio, also referred to as the compartment equivalence ratio. The global equivalence ratio is defined as the mass of fuel introduced into a controlled volume divided by the mass of air entrained, normalized by some stoichiometric value of fuel to air. In other words, the uncombusted and combusted fuel to air ratio normalized by the stoichiometric ratio of that fuel to air. Some experiments determine the global equivalence ratio using direct measurements of the rate at which the fuel source is introduced into the enclosure. The mass flow rate of fuel into an enclosure is dependent on the state of the fuel. When using a gaseous burner, the mass flow rate of fuel is defined as the mass flow rate of fuel into the burner, typically maintained by a mass flow controller. In instances where the fuel is a liquid or a solid, the mass of fuel is defined by the mass loss rate of fuel measured using a load cell. The mass rate of air introduced in some control volume has been estimated from a few different analyses. In order to calculate the maximum vent flow of air into an enclosure, some work has used Babruska's expression. Some works have measured the equivalence ratio through the use of a feed meter. Originally developed by Babruskas, a feed meter is a continuous sampling device designed to measure the global equivalence ratio via an extracted sample obtained in a homogeneous region. The concept behind the feed meter's initial design was to sample a portion of a well-mixed exhaust within an enclosure such that the ratio of all combusted fuel and air normalized by the stoichiometric coefficient of the parent fuel could be determined. When using the feed meter, it is best to think about it as a local measurement. In certain cases, people have used the term local equivalence ratio loosely, possibly creating some confusion. Although the feed meter can measure a global equivalence ratio, it is from a local regime, such that an extracted gas sample is only from a small portion of the entire controlled volume of interest. Over the past few years, I've had the pleasure to work with Tom Cleary at NIST on the design of a second-generation feed meter. The second-generation feed meter is similar to its predecessor in that it can measure the global equivalence ratio from a local regime. This is achieved from gas samples extracted from a local regime via a vacuum pump. Upon extraction, gas and particulate samples are fed into the feed meter's reactor, enclosed in a high-temperature tubular furnace. This reactor includes a quartz tubing packed with some combustion catalyst that's heated to approximately 750 degrees centigrade or higher. Excess oxygen is also introduced into the inlet of the feed meter. The addition of oxygen to the incoming mixture, combined with the presence of a high-temperature combustion catalyst, allows for lean combustion within the reactor exhaust exclusively comprised of oxygen, carbon dioxide, water vapor, and inert gases. In its previous iteration, the combusted gas sample exiting the reactor is dried, then fed into a mass flow meter and gas analyzer to measure the flow in oxygen and CO2 concentrations. Those measurements are crucial to calculating the global equivalence ratio. In the second generation feed meter, however, flow is controlled by a high temperature mass flow controller located at the outlet of the reactor. The utility of a high temperature mass flow controller in the second generation feed meter is its ability to maintain a consistent mass flow rate at the inlet of the feed meter while being heated. Because it is heated, the mass flow controller can maintain water vapor that's generated from combustion when inside the reactor, meaning it is accounted for when measuring the total flow through the feed meter. Through the addition of oxygen concentration measurement at the inlet, the true equivalence ratio, or that original definition that I showed of actual fuel to air ratio relative to the stoichiometric value, can be calculated. This equivalence ratio measurement is agnostic of the parent fuel composition, meaning that an unburned fuel and air equivalence ratio can be measured in real time using this technique. Many experiments have applied the feed meter to measure the global or local fuel equivalence ratio. When I say local fuel equivalence ratio, I'm referring to the original definition of unburned fuel to air ratio normalized by some stoichiometric value. Most recently, the local fuel equivalence ratio was measured in a series of backdraft experiments conducted at NIST. Using two feed meters to sample at various positions, the local fuel equivalence ratio was measured in real time in an isolated enclosure that led up to a backdraft. You can see on the plot on the right of the slide that for cases with methane, there is a rich mixture in the upper layer, which becomes leaner lower in the compartment. For propane cases, the fuel mixture is more evenly dispersed as time increases. Many works have used mixture fraction to establish the equivalence ratio and correlate it to species generation. Mixture fraction is a non-dimensional quantity representing the mass fraction of species derived from the fuel stream. In practice, mixture fraction is determined from mass fraction and molecular weight of species containing carbon, based on Peter's definition. If you look to the plot on the right, you can see that experimental results are compared to some ideal state relations shown in lines. The benefit of mixture fraction is that if you can determine its value, you can compare or estimate species generation based on the ideal state relation. In the context of the equivalence ratio, there was a relationship that linked the compartment equivalence ratio to mixture fraction, as shown by the definition towards the bottom of the slide. The correlation between species generation and equivalence ratio traces back to a series of experiments deemed Hood experiments. These experiments include experiments conducted by Byler, Sittigen, Lim, Toner, Zukowski, and Morhart. The primary objective of these Hood experiments was to establish a correlation between carbon monoxide yield and ventilation within the compartment. Byler's experimental setup, shown to the left of the slide, was unique in that the height of the hood could be modified relative to the distance from the fire, thus controlling the rate of air entraining through the hood. Temperature and gas species concentrations were measured further downstream in the duct. From these measurements, Byler observed a fuel-dependent correlation between CO production and the global equivalence ratio, whose generation was faster under fuel-rich conditions. It was also observed that CO yield remained constant when the equivalence ratio was greater than 1.3 or less than 0.5. Toner, Morhart, and Zukowski expanded upon Byler's work by expanding upon the experimental approach. Toner refined the experimental procedure of the Hood experiments by improving the species concentration analysis using a gas chromatography. Morhart and Zukowski applied the same measurement techniques as Toner, but using a new Hood facility. In those experiments, the experimental setup was designed to model conditions expected in a developing enclosure fire by allowing air to be added to the upper layer, defining something called the upper layer equivalence ratio. The experimental setup of Morhart and Zukowski is shown to the left, in which air can enter the upper equivalence ratio while a fire is burning underneath. By their definition, the upper layer equivalence ratio here is defined as the mass originating from fuel to all air within the enclosure, or the controlled volume, normalized by some stoichiometric fuel-to-air ratio. Motivated by the Hood experiments, Pitt adopted experiments of his own, exploring mechanisms of CO generation that resulted in the development of the global equivalence ratio concept. In this concept, Pitt proposed that the CO production correlates to an enclosure's equivalence ratio and is generalized to different fuel groups with a caveat that it does not account for certain mechanisms. These mechanisms include quenching of a turbulent fire plume when entering the upper layer, mixing of air into the upper layer, the pyrolysis of particulate matter in a high temperature oxygen depleted environment, and the additional generation of CO in the upper layer that's attributed to kinetic interaction driven by high temperatures. Pitts then later developed an algorithm that accounted for all these mechanisms to correlate the equivalence ratio, global equivalence ratio, to CO generation. However, he revised the algorithm later, acknowledging that air entering the enclosure is not fully molecular mixed with gases in the fuel-rich upper layer, and that a significant portion of air that exits the enclosure is not accounted for. Pitts also examined CO concentrations at different isothermal conditions using a bench scale plug flow reactor with a constant equivalence ratio of approximately 2. He found that temperatures below 800 K result in an unreactive gas mixture where CO and CO2 are frozen out. Temperatures between 800 K and 1000 K cause a faster reaction rate, leading to a faster oxidation of CO. He also found that temperatures above 1100 K enabled a much faster reaction rate and higher CO production. Accounting for the influence of temperature, Goddick and Latimer established a methodology to estimate species yield. The methodology also incorporates the effects of oxygen-deficient smoke layers and species transport based on the compartment hallway experiments conducted by Goddick et al. The experimental setup of these compartment experiments is shown to the left, in which air is introduced at the bottom of the compartment below the fire. A key component to Goddick and Latimer's methodology is the fuel-independent correlations between the equivalence ratio and unnormalized CO yields. The figures are shown on the right of the slide show the CO yield correlations relative to the equivalence ratio. It also is fitted to experimental data of Toner, Morhart, and Byler. The left plot presents methane CO yields as a function of the equivalence ratio studied by Toner and Morhart. Goddick and Latimer concluded that the collected data falls between both curves since these fires had temperatures between 490 K and 870 K, within the transition range between 800 K and 900 K. The right plot of the figure compares hexane data obtained from Byler and Goddick and Latimer and shows the correlation is a better resemblance of the experimental data, which is expected given that the correlations were established from these data sets. Looking at bench scale experiments, Torsen established fuel-dependent correlations of CO and soot generation efficiency relative to the equivalence ratio using work conducted at Fatschroot Mutual Corporation. Torsen defined generation efficiency as the ratio of species yield between ventilation control and well-ventilated environments. The correlations were established from datasets involving 6 common synthetic polymers and pinewood fuels burned in a fire propagation apparatus shown on the right side of the slide. Torsen's expression for CO and smoke yield is the same, and the equations are shown in the upper left of the slide. The only difference is that the coefficients vary based on the material or based on the yield of interest. Yields of fire products for well-ventilated fires obtained using the fire propagation apparatus is reported in the SFPE 4th edition handbook. Other works, however, have shown that the yields of fire products such as CO and soot can vary at larger scales. In this slide, we see a purser furnace, which is used at bench scale experiments, focusing mainly on toxic combustion product yields. This apparatus was developed to decompose test specimens under flaming combustion conditions by varying the equivalence ratio via airflow rates and temperatures, allowing product yields to be measured downstream using various instrumentation. Several works have utilized this solid-state tubular furnace, also known as an ISO standard, to estimate variations in lethal toxicity and other toxic combustion products from different materials. One significant result of the use of a purser apparatus is Purser's comparison of his CO yield measurements using the solid-state tubular furnace and comparing it to different scale experiments. The results are shown in the figure on the slide, which shows CO yield data as a function of the equivalence ratio for all experiments, where each plot corresponds to the burned fuel. To compare CO yield data, Purser used either a sigmoid-Weibull or exponential or linear regression fitting of previously recorded data. This figure also includes Torsen's correlation for experiments utilizing either propylene or polyethylene, pine wood, or PMMA. Goddard's correlation is not included since they were developed from non-oxygenated fuels, such as the ones shown here. In fuel lean conditions, Purser's fitting and Torsen's correlations fairly complement the experimental dataset. There is a growing discrepancy, however, for most presented correlations under fuel-rich conditions. The limitations between Torsen's correlations and other datasets for underventilated fires have been discussed in previous works. For Purser's correlation, although it is concluded that the bench scale measurements match some of the results from larger scale experiments demonstrating the significance of the equivalence ratio relationship to CO yield, it is acknowledged that other contributing mechanisms to CO generation are unaccounted for and may attribute to observed differences. There are several definitions and measurement techniques for the equivalence ratio, which corresponds to the ventilation in a controlled volume. In several instances, the equivalence ratio has been used as a metric to predict toxic combustion product yields at varying ventilations. Although some correlations have proven to fit previously collected data, there is little discussion on the limitations of these correlations, mainly in fuel-rich environments. One big takeaway is that the equivalence ratio is a piece of the puzzle to predicting toxic species yields by quantifying ventilation, but does not capture the entire physics of the fire phenomenon that generates different toxic species.